Greetings, gentle readers, curious fellow earthlings. Reading Foundations today, August 6, 2026, with Ross Finlayson and myself. Will be, of its usual course, a consideration of foundations and influences and references, and delving into the box of books, the stack of derivations, and these sorts of things. The previous book being looked at was 500 Years of Printing, or this S.H. Steinberg's account of the history of the printed word, or about 500 years worth of it, since the invention of the printing press. When that book was published, it would have been about 500 years since that. So later in this box of books, there will be some more of about that account, and then some varia, and then there's not much left in this box, and diving right into the next box of books. So what I thought to mention today is an account of some references and some influences and some attributions to the field of mathematics. So in the Musitorium playlist here on my channel is that I selected a few videos from some eminent mathematicians to consider. And so who these are, their accounts, and they're mostly sort of blackboard accounts or presentations. There's Dr. Terence Tao, one of the most eminent mathematicians in the world, and in some accounts, one of the greatest mathematicians in the world, and Professor and Dr. Terence Tao. And then there's a Professor and Dr. Timothy Gowers, also considered, from having the Fields Medal, one of the most highly esteemed honors given to mathematicians who perform works relevant to the advancement of mathematics in a global sense. And then from Professor Dr. Leinster, whom I'm not quite so aware of yet, is deemed kind of the same class, and that these individuals are of a sort of the same class from the same time, and it's about the same time as my time in a sense, contemporaries, if not necessarily not running in the same circles by any means. Yet kind of in the same sphere and of the same account of an amount of life experience in a sense. So that I find these kind of relatable in a sense. So what these are, these four videos, and two of these video essays are from Dr. Tao, one about infinity and arithmetic, and the other about continuity and analysis. Then this third essay is from Gowers, is about infinity and algebra. Is kind of how I'm framing it. And then this fourth video from Leinster is kind of continuity and entropy. And so this is kind of how I describe my perspective on what they're talking about, and the issues and the conclusions and the definitions and these sorts of things, what go on in them. So in this first video, it's about arithmetic progressions. And so these are accounts of what happens at infinity. There are conjectures like the Goldbach conjectures or the twin primes conjecture, and other accounts of, since Erdos, the prolific number theorist, who brought many accounts of both constructions about the infinite and the density of the primes, or for counting arguments of many sorts, and these sorts of things. And then for Andres Szemeredi, who has some theorems then for things like, well, for Riemann-Roch theorem, but then it's talked separately about like Roth theorem, and then for accounts of what are these fundamental building blocks, making things for estimates and error bounds, and the modeling of error bounds of approximations of the densities of given subsets of the integers within the integers, or distances within the integers of particular structural multiplicities or properties, often related to factorizations and sums. Vis-a-vis the p-adic integers, which basically have multiplication on the high end and addition on the low end, and these sorts of things. So in Dr. Tao's account of his developments and an impromptu and sort of spontaneous account of development on demand in infinity and arithmetic progressions, and then it's related to arithmetic in a sense. And what gratified me about his presentation was that he immediately begins to explain that the accounts of the examples and the constructions and then immediate counterexamples begin to abound. And he describes the narration of the course of development of what goes on in the intuitions, and then what's attained to, and what's obtained, what's considered constructed, and so. So when talking about that, the independence of certain number-theoretic conjectures due to their being or not being a standard model of integers and ordinary model of integers, have that the independence of these conjectures have that various competing rulialities, here about well-foundedness, well-ordering, and well-dispersion for theories with a set theoretic perspective, or an ordering theory perspective, or a category theory perspective, basically, have that those are different foundations, they're rulialities. And so the independence arises that the inductive of results that are strong in one of those theories for its own elements are weak in the other theories and their models of the other theories' elements. So the independence leads to that then there are counterexamples brought that extended make contradictions. And so it gratified me that while Dr. Tao was making a development in this account of arithmetic progressions, he also introduces to be set aside and not discarded and just ignored these counter developments, these what would be counterexamples, and these sorts of things. So without necessarily so explicitly mentioning the giant monsters of mathematical independence, he details some of the surface, the topography of this atlas of mathematical independence and mathematical completeness and mathematical repleteness. So in that sense, then, I kind of framed that first essay as an account of infinity and arithmetic, and the ordinary and extraordinary. So the second video is also from Dr. Tao, and what it's about is continuity and analysis. And so as it begins to be presented, he gives a great overview and a side-by-side comparison of matters of the discrete and matters of the continuous. And then he goes on to describe that ultra products are basically this idea of there being various models of continuous domains. Here in the theory, those are primary, that these line reals are primary, and then the field reals are derivative, and the signal reals are derivative. Then that there are also ways to look at them as each primary on their own accounts with regards to ordering theory for line reals, set theory for field reals, and category theory for signal reals, in a sense, loosely, yet as well concretely and structurally. So Tao helps establish that ultra products, and then for ultra filters, have ways to talk about things that are continuous in the higher level of the analysis then, and making for measure and accounts of measure theory. It makes for the mensurable, what's measurable, after something that's quantifiable, like the integers, and then what's measurable is like geometries, the area and the continuous. Analysis is realm, in a sense. So since here the foundations are about infinity and continuity is kind of primary, then I found these reflective illustrations and presentations very illuminating because they bring the intuition to the room. And so one of Tao's concepts he has is called hard and soft in mathematics. The hard or sharp, as it's sometimes put, is that which is constructive and basically is more the constructivist variety. And then the soft is relating the things that would be these matters of mathematical independence and the intuitionism, and that is they turn each other over, the hard and soft, and the constructivism and the intuitionism, that there's the account that terms like general and abstract and even classical and these other notions of definition have that their opposite meanings are also the definition. Here, for example, from the comment about monodromy and holonomy, and about how differential geometries account as, from the inside, the opposite of the way that the analysis would look at that. Just making it so that the wider fuller dialectic has for perspective and projection that there are these lenses in the mirrors of these accounts, in these deconstructive accounts, that have it that these essays, as were kind of selected after some time of considering the opinions and statements and presentations, which were widely available in a great multitude from these researchers and theorists in mathematical foundations, as they would be, the derivations and the theory, that these accounts then of infinity and arithmetic and independence, and then a course upwards for at least one regular account, and then continuity and the development of analysis and independence has that then these are considered informative and deftly introduced or mentioned, and not merely excluded or ignored the invincible ignorance of the inductive accounts, the weak induction in the accounts, for accounts then of the strong induction in the superclassical. And one thing to mention about that is the difference or the presence and relevance of terms the almost and the very. So the other day there was a news article, and it was something along the lines of, well, one of the AIs came up with that it's made a brief proof that it took group theory and accounts of homomorphisms and accounts of a regularity lemma and took what was being used to hold up that groups are sofic and so that finite approximations are complete, had a counterexample deftly in the theory. So what this does is kind of like Gödel's incompleteness, or otherwise Miramenov's extraordinary, a constructed result like Russell's paradox, before Russell's retro thesis to ignore this in its isolation and significance. That the account of mathematical independence is being found again and again in all these many ways. And so when hearing something about that and how that basically blocked or rejected a whole bunch of conjectures which otherwise rest on this regularity lemma of sort, for things like fixed point theorem, vis-a-vis compactness, and the lack thereof of those properties according to regularity lemmas and compactness theorems and completions, has that this is a sign of the times that these independence results are then having that, for example, the massively produced and sometimes overproduced accounts of the AI developments in these fields are contingent on their implicits, these assumptions. And so the account that, well, the latest, greatest AI thing, at least from this corner, is that it's not so, that approximations are not complete, that the almost and the very don't always suffice, is then telling that many of the accounts you hear of, like AI proved this or AI proved that, long-standing open conjectures, has that it's just made it more conjectures, not so much close the old ones. But at the same time, it's also held open or broken open some of the old conjectures, not so much what's been accumulating with regards to these things. So good news in just this ton of news. Relating that to then the developments in the historical development of individuals in the field of great publicity, the accounts that these are already known things, if less so well known. All right. So infinity and arithmetic, then continuity and analysis. So Dr. Gowers, he then talks an account of more about the arithmetic progressions and Szemeredi's theorem. Yet the account he makes is of all these different kinds of proofs that get to arriving at it. So this is more infinity and algebra is the way I'm looking at it. Because each of these different proofs has different algebraic settings that kind of bring together these magmas, which is a looser form of algebra, more inclusive, more general, or less specific, or more specific and less general, alternatingly, magmas and algebras. And here that's kind of addressed about the rational algebras and rational radical magmas, and discuss quite a bit more in extent the account of the almost is the not quite, and Falting's purity and Falting's dirty. Before I might have said Falting, it was intended to reflect that the almost periodic and almost respectful is another new one. Almost everywhere or almost all is in many cases not quite, and so is to be made an account that then as well for things like the ultra products and ultra filters, which is said to say that, well, if you can make a rational approximation of something that's dense, then there's a continuum limit and it's dense, and furthermore it's complete, and then it has measure. The stronger induction, after an inductive limit, making an infinite limit, and then a continuum limit. Here that's only after an account that must follow some superclassical result that already exists in mathematical Platonism. So that would be for Zeno's arguments first, the geometric series, the half and half and half again, their sum exists, the limit, and that it is a sum, to give a case for strong induction that the almost is not quite here is so. And like the accounts like, well, the non-sofic groups exist, says that's so. It's well to know then that in many cases it does suffice. It's close enough when almost all is close enough that it yet reflects on that has a continuous topology, its own initial and final topology, and a lot of other things that keep this analyticity thoroughly engaged. So Gowers' story about the development of different approaches of proofs in the algebraic, as I put it, like for Furstenberg and these other accounts for Szemeredi's theorems. And he was a close collaborator of Szemeredi, who is still impactful in the many developments about these conjectures and the open issues where these openings, catastrophes, and perestroikas are singularities in a singularity theory, yet branches in a multiplicity theory. That's how I frame that third video there as considered. So infinity in arithmetic, continuity in analysis, infinity in algebra, and then this fourth video or Leinster's about entropy. And so entropy is an account of many things. And so he talks about entropy in information and introduces that it comes from many fields. So this is more about the continuity in signals, because the definition of entropy in information these days, it kind of follows from statistical mechanics after Kelvin, being that the principle of least action and thermosecond law is where the statistical ensemble and what made for the accounts after Boyle's law and ideal gas law. And here the molar gas constant is a mathematical constant that's a part of the Boltzmann constant and has to do with the Planck constant, Boltzmann constant, and otherwise with regards to statistical mechanics. About how that's put together is that entropy, besides thermosecond law, then has all these great accounts from information theory, and as well that information comes from language theory as well. So Leinster's presentation there is fantastic because he helps show that entropy, its definition, and information, its definition, comes in from a lot of these angles. The kinetic and the statistical ensemble, signals and sampling and reconstruction in theory, and then as well probability, and then here besides is in language and words, information. So continuity and entropy then is for continuity and signals as well. And so that there's kind of an essay account of this infinity in arithmetic, continuity and analysis, infinity in algebra, and continuity and analysis again. So that's just what I thought to mention of my reading and my impression of these as if not necessarily what you'd kind of find on the front page, yet in their kind of in their backlog of these their presentations, talks, essays, discussions of these individuals who are great and very well renowned and deservedly so. Then that what can be taken away from them from this sort of deconstructive account and from mathematical foundations is the acknowledgement of the greater sort of fuller dialectic, and are the signposts that show for these developments in the fields, then that the many conjectures are yet having that the modern account that makes the ready induction is yet subject that it's weak induction unless it's strong induction, and it's a soft or not a sharp limit unless it's a hard limit or a complete limit in a sense. So by looking at these sorts of accounts and relating them thusly, what here is sort of a much simpler account, accessible and available, yet talking to all these things is that ultra products and ultra filters way at the top of mathematical analysis are just these continuous domains. The various counts of the independence of large, larger, and largest laws of large numbers decide various cases and in these counterexamples, counter-developments and counterexamples, providing reasoning why to make for Erdős's giant monsters of mathematical independence, usually about infinity, that there's this great atlas of mathematical independence, again about infinity and continuity. Then the accounts for entropy has that is shown that these different fields of analysis again have their partial and attaining to the complete towards each other, and then that in the limit they're said to meet, about how it's distinct their origins and how and why they come together, that they can be decomposed and made for deconstructive accounts, why it is so, that thusly this survey of the modern account of the state of the world, of the state of affairs, of the opinion in not just popular mathematics but premier mathematics, that it is so that there are ready ways to both use the accounts of the developments of an axiomless geometry and an axiomless arithmetic, then for algebras and magmas for arithmetic and algebra and then analysis. That then topology and functions are more the flexible realms of definition, and then that the operator theory makes for the accounts of and for category the kind of the method of these analytical bridges that are super classical results, and their classical readings and these sorts of things. So that's when I encountered those videos and why I selected them. What I thought is their relevance and their particular importance because of their style and their content and the fact that they introduce kind of the boundaries, including that the boundaries have their own extents that are also infinite and continuous. Then about the lenses and perspectives and the mirrors and the reflections that are as for these complementary duals in a world of competing claims and competing rulialities, the paradox-free reason and these sorts of things. One other comment about entropy is that it's got two definitions anyways. So Aristotle's entropy is what goes up must come down, and then Leibniz's entropy is that organization and systems maintain homeostasis, so they go on. And so these are basically two entirely opposite accounts of what entropy is. And so that can be framed in the absolute and relative, or the local and global, and these sorts of accounts. Just going to show then when they meet in the middle, what inductively any of either ways from the invincible ignorance of inductive inference to inductive impasses, then the only way they can cross is some superclassical result of an analytical bridge in the middle. The a priori was put by Colley and is after Poincare and Gonseth and Husserl and, or not Husserl, but Bernays and Hilbert in the foundations of mathematics, and for a postulated continuity of Hilbert that makes for the principle of perfection of Leibniz. That these are the accounts here that help to show that besides that they've come together in the reductionist sense, they also come together in the anti-reductionist or the holistic sense. Instead of making for fragmented pluralism, because these counterdevelops and counterexamples disprove each other according to weak inductive accounts these ways. That they do have stronger analytical results for strong induction and the availability of strong induction, and the ex falso nihilum, the resistance to meddling, and the fact that it can be a consistent theory instead of fragmented pluralism or the synthetic or the silly, as sometimes it's put, or these sorts of things. So that I thought was illuminating, and helps to establish that then the various trails of these things has that they're different mountains, but they're all part of one range in the sense. Well, then into the box of books. This box of books. So this after the previous talk, there was this 500 years of the printed word, 500 years of printing. And then this book is called The Printed Book in America by Joseph Blumenthal. So what it is basically a history, a survey of the printed book in America. Published for the Dartmouth College Library by the University Press of New England, Hanover and London, 1977, 1989. The colonial period, the 19th century and into the 20th century, the Renaissance in American printing in the 20th century. So this is basically of the industrialists and about then the publishers and the development of these kinds of things. The growth of industrialism during the 19th century and the enormous economic expansion after the Civil War gave rise for the first time in the United States to society with the means and leisure to enjoy some of the amenities of older civilizations. In 1884, a group of dedicated book collectors founded the Grolier Club of New York for the literary study and promotion of the arts, entering into the production of books. The arts and crafts which burgeoned during the late decades of the 19th century found their counterpart in an extraordinary gathering of typographic genius in New England, an heroic generation of designers and printers whose work is probably being called a renaissance of fine printing in America. What is fine printing? Fine printing involves an aesthetic dedication and an expression of the human spirit, which through the arrangement and presentation of the printed word, reaches towards order and harmony and beauty. Fine printing applies scholarship, artistry, and craftsmanship at the command of the practitioner, whether in printing houses, at private presses, or in workshops of college art departments, whether on automatic machinery, on hand equipment. Such are the criteria by which the books discussed and reproduced in the volume have been chosen. So then this has encountered many presses, and their books and their works, and about the papermaking and the printmaking process itself, old papermaking, literature of papermaking, primitive papermaking, the papermaking pilgrimage, papermaking, and these sorts of things, vis-a-vis the modern accounts and the digital, and that I'd wonder where it ends if it basically mentions is with regards to that. Papermaking by hand. Not so much. The art and elements of lettering. So anyways, this is a survey of printing and publishing of quite a long time. Then this next book here, let's see here. Now this is basically of the random or varia. And now I'll have a difficult time transliterating and pronouncing this name. Krzyzanowski. K-R-Z-H-I-Z-H-A-N-O-F-S-K-Y. Sigismund Krzyzanowski. Translated from the Russian by Joanne Turnbull. Memories of the Future. Let's see what the back cover has to say about this. Krzyzanowski is a poker-faced surrealist whose imagination is so radical it goes beyond political lampoon into the realms of metaphysical assault. His writings is in the fantastic modernist mode of Jorge Luis Borges and Stanislaw Lem. He works out the eccentric premises of his plot with a relentless cogency. Written in Soviet Moscow in the 1920s, but considered too subversive even to show to a publisher, 7 tales included here attest to Sigismund Krzyzanowski's boundless imagination, black humor, and breathtaking irony. A man loses his way. Stories about a man. So these are short stories. NYRB Classics Literature. New York Review Books. So this was published in 2006 and 2009. Then I'll set this aside. These are stories. Though I'd wonder if they speak directly to philosophy. Optically, this is entirely possible. Then once the machine is in operation, this invisibility should gradually spread from activator to activated. About the temporal selector is what he calls it. Were it possible to detach the auditory nerve's internal ending and graft it on the brain's optic center, we would see sounds, and given the reverse operation, hear shapes and colors. So here, I don't know if that would be the greatest sort of idea, although I do tend to kind of neglect my sense of smell to kind of keep it from occupying my brain, and I don't consider it particularly relevant to stimulus because for example, it's something that kind of overpowers the other perceptions and the limbic reflexes and the gastrodigestive reflexes and these kinds of things. But all the senses touch all the senses is a usual enough idea. Speaking in more modern terms, he flicked the wariness from his brain like the dust from a hat. He understood all the words that had been said to him, yet he didn't understand their meaning. How could something lesser block the way of something greater? How could their minor revolution impede his major one? The one he carried between his temples, the one that was above all that was above. What could they do? So he's got a very interesting account of the reflective. Krzyzanowski. Then the next book in this box is André Vandenbroek's, Vandenbroek, Philosophical Geometry. So here there's an account of axiomless geometry and total geometry vis-a-vis the partial geometry, matters of perspective and projection. Here's a figure 6. It's a lattice square 3 by 3 with dashed edges beyond the edges indicating it's part of a greater lattice. More figures like a dot in the middle of a page. Harmonic proportions of the 7 shortest string lengths, table 4. So this gets into combinatorial enumeration and the harmonic functions, and so the geometric and arithmetic and harmonic and what those intend to entail. About then the combinatorial enumeration or combinatorics, counting arguments, permutations, Stirling's numbers, cyclone subset numbers after Pascal, or the choice numbers, after the binomial theorem, and accounts like that. Then make also for things like Newton's development of what are telescoping infinite series and the like. Legendre polynomials and these sorts of things, the many kinds of those, and how those result fractions and series and these sorts of things. Harmonic string length. Now this will be interesting to me because I've been studying text on the computer and these sorts of accounts of the this scalar-wide vector word character machine to make for accounts of standard algorithms of find. Here that there's basically find first and find long as an account of it's somewhere far away, find it. And then find next, find plex, like it's right here, find it and all its alternatives. So kind of far and near, find first, find long, and find next, find plex. And then how then these standard algorithms kind of implement this from these decomposed patterns for exact substring match or by character classes here. That there's this SA for standard algorithm, SA free one, which is just a character class for one character and an anchored offset, and then free stars, which can basically take a partition like A star, B star in the language of regular expressions, and find where there is in the middle of where that it matches, and that there is the partition or boundary between those two, and it does that in parallel, and it does that also in constant stallless, branchless, callless code. So the findings happen that way, and then the matchings can be interpreted according to the higher level of functional routine. For contrived inputs that both provide linear speed up and linear breakdown speed up of various otherwise serial algorithms, courtesy the serial layout of text and patterns called text cells for text elements and patels for pattern elements. That's kind of what I've been looking at. So here, though, it's this harmonic string lengths for philosophical geometry, and harmonic progression exists as a series of nodes on a vibrating string. This makes a great account for periodicity and the difference between when you think of text and letters, like when they're in Unicode or UTF-8 encoding, meaning that many of the letters fit in a small alphabet, like A through Z. And then some of the symbols or characters are like an emoji from way down the page of it. So it's smooth when the codes are small and uniform. And then there's a bump whenever there's an external character. Then it's gritty when there are a bunch of those, and then it's rough when it's very irregular. And so the difference between the smooth, bumpy, and gritty and rough is either way the regularity of this harmonics and applying the periodicity to these strings, and then for their length that it really suggests about the Legendre and then Laguerre and the other Frenchmen that make all these accounts of the rational interpolations and extrapolations of these things. So the author here, Vandenbroek, is getting into this and relating it in an idea to a vibrating string. As such, as representation is a segment of circle stretched between an extreme fixed point P on the left and an extreme movable node A to the right. So it's more like we consider it more of a mass spring system than a string system. Thus, if in theory B less than Q less than A progress harmonically, then in practice BQ less than PQ less than PA, setting up a system of inequalities. And then he says, whereas in theoria, the harmonic measure between two terms A and B can be shown by means of these two extremes to reside in a mean term, 2AB over A plus B. In practica, four nodes are providing the intervals PA, PQ, PB as three different string lengths, PA being the unitary string, while the small length PB as well mean like a fraction there. So this is a great sort of account because these are truisms, these are facts. And then it's underexplored, it's underdeveloped how that happens. because the usual accounts then of whether, well, it's a linear and we're dealing with lengths, and vis-a-vis that when we're dealing with modes and the like of repetitions and patterns, about patterns and sequences, has that this is just a good example of quite profound bit here just from reading this page or so. Harmonic proportion, geometric measure, and harmonic proportion. Usually the account of the arithmetic and geometric and harmonic mean is also built in a system of inequalities. Here was Kazarinoff, I believe is what was read here, as part of an account of functional analysis or into the number theory, was developed about the arithmetic and geometric and harmonic mean back in the talks about this descriptive differential dynamics, which is sort of a second course of the development of descriptive differential dynamics after a degree that includes the usual course in ordinary differential equations, boundary value problems, and so on, and numerical methods, and that. Has that the geometric and harmonic and arithmetic means may admit violations of the inequalities. And so there are reasonings here that then to formally give a reasoning here for Van den Broek why his geometric measure and harmonic proportions in those, how they can make accounts of the constitutive and reconstitutive that would keep the whole thing in order. Has that there are ways to find some of what are uniqueness results on the uniqueness of accounts due to the harmonic are distinctness results, speaking to this great account of mathematical independence. These aren't things that break abruptly. These aren't things that happen out of nowhere. These are things that happen due to the entire systemic account, the super classical, and then that they do. That the vibrating string, for example, with its different accounts given by Euler and others that disagree, and were found, following Euler's account, to be whether the string is plucked and gets displaced horizontally or only vertically. That one or the other of those essentially didn't add up. And just showing a counter development and counter examples, so that for something like Euler's great account of the infinite series and for the Eulerian identity and all that kind of stuff is not the only game in town. That is it is simply a branch in what's the multiplicity theory, not a singularity in a singularity theory. It is an opening. These are other examples that anyone can find in the literature, and many practitioners of mathematics stumble upon and wonder about all the time. That there are also ways to help cross those analytical bridges, to find them, to match them, and to cross them. Rational angles show the complementary relation. Here, the linear fractional equation is an integral equation. And so then it's followed in the development of integral equations by Clairaut's equation and D'Alembert's equation, the integral equations. So this identity dimension I found out is also being considered some things called strictly positive or totally positive in the new mathematics language of the day. And so some of these accounts of like symmetry is about that, and analysis about that. Besides like the semi-infinite account of Wigner or I'd be better prepared to find or recall the fellow's name. Besides Wigner, and I will, and I mentioned it in an earlier date about the identity dimension and the totally positive and this kind of thing. Has that there's the accounts of the semi-infinite, and that these are that complex analysis is not the only game in town when it comes to analyticity and the integral calculus and the differential calculus, and the different integral and integral differ. So anyways, that the identity dimension is the envelope of the linear fractional equation and Clairaut's equation and D'Alembert's equation. Geometric measure and harmonic proportion. So this is a great little book, and it's got stuff that is It's higher mathematics is what this is. The cathetus and base. Thus an angle never exists in isolation, but within the system of the three angles of a right triangle whose right angle stands for the possibility of measure, and the third angle is complement to the measured angle. Within the measure, this complement expresses itself as an inverse relation. For if the measure of an angle is expressed as cathetus over base equals b over a, then its complementary angle within the right triangle will be expressed as cathetus or cathetus over base equals a over b. In the measure of angle 1, where a equals b, there's identity between complement and angle, and the footnote indicated, so the duality retracts into unity. But in all other angular measures, the angle is inversed into its complement. And because the angle by definition is a fraction of unity, the complement is always greater than the angle, and thus creative of pure multiplicity. This is a sort of a kind of stunning statement. And here is framed like this. So Euclid's axioms have that there are the postulates, and they're generally going to be 5 postulates. And so the one that is ever let out to make the super Euclidean is called the parallel postulate, whether infinite parallel lines meet at infinity or not. Then here, there's mention ever since reading something like Wertheimer's book about the arcangle formula, and the idea that the internal angles always have that they sum to 2 pi for a circle. The internal angles of the polygon sum 2 pi. So this is, I think, from the Logos 2000 about space inversion, and helping establish why that is so compared to otherwise the usual formula, and why the thinking that goes into it is counterintuitive. Has this. So there's an implicit axiom of geometry called this double angle axiom. So this is parallel postulate, and then parallel infinite lines don't meet, and then that a straight line makes 2 angles. So I'd relate this to Vandenbroek's here account of angle and complement. Looking for a name about how he relates it to the pure multiplicity. And so again, this is another story about things like the roots of unity and the roots of 0 here, as it's put sometimes. And our 3 laws of infinity and 3 laws of 0. And then this account of geometry and for space inversion after Wertheimer's productive thinking. Then this account of Vandenbroek I value. I'm going to be looking at this. I'm going to reading this for a while, because then besides this prose of the first 40 or 50 pages, thoughts on scale, hypotheses, logical universe. Logical universe has pre-existence and then the universal language, logos in the word and the definition, syntactic subterms, then presence and reality. Language as pre-existing is logos. I hear it pronounced logos sometimes, but I'll just say logos. The pre-existing presence of language structures the logical universe into ordered sets of terms, which are so many fragments of reality. See, the ordered sets is already kind of 2 theories in one. But at least it's not one without both in these kinds of things. A postulate of existence concerning an entity definable by the logical representation is not necessary to philosophical geometry as it is to metaphysics and other non-geometric philosophies. Philosophical geometry admits language as preceding its discipline. It concedes pre-existence language, thus giving it term place. This is a great book, and I really have to agree with this. I'm gonna read Andre Vandenbroek's Philosophical Geometry quite a bit more, and I'm very glad that I paid $3.99 for it. And this copy is mine. The last book in the box today is Barry L. Holstein's Topics in Advanced Quantum Mechanics. So before we get to advanced quantum mechanics, and first kind of have to get to quantum mechanics. Before you get to quantum mechanics, you kind of have to get to classical mechanics. Before you get to classical mechanics, kind of going to have to get to mechanics. Before there's mechanics, there's kind of statics and dynamics. And topics in advanced quantum mechanics might have suggested, for example, the representation theory and the algebras. I think the Virasoro algebras and about the magmas and so on are kind of a fertile field in that sense of the algebras and representations, represent theory, representation theory. I'm trying to remember the name of the particular author I was reading from quantum theory, who's about algebras and then also permutations, and then he describes how the inverses come out as after the identity matrix and the non-invertible, the case where there's kind of a non-invertible singularity that is the result of inversion. And so I will remember that name. And maybe I'll recall it from watching some of the previous essays that kind of had as the subject matter the quantum. But it was in the contents of Sachs and Slater, or structural chemistry and nucleonic nuclear theory, about a book on group theory or algebra with regards to quantum mechanics. Then separately about quantum mechanics, you've got the difference between classical mechanics and things like Born and Feynman, or for the commutator rules and the propagation laws. So those are as for what are the classicals, where those are commutation rules and propagation laws, and what are the quantum, where those are non-commutative, the commutator relations, and scattering and tunneling, the propagation laws. So that's quantum mechanics. And then classical mechanics involves, of course, the account of Galileo's laws and Galilean invariance before getting into like relativistic invariance and Lorentzian invariance. And before getting in, besides that, separately, the quantum mechanical. And then bringing those together, Reichenbach. My opinion of Reichenbach is much improved since looking at philosophical foundations of quantum mechanics. Because I had him as an empiricist, I thought, because he does write some things, kind of like talking about the non-sofic groups. He was like, well, the cumulative limit theorem, there's the central limit theorem from probability theory, can be said to be this strong, and which I don't agree with, because I got three limit theorems: central, uniform, and polarized. And so these accounts then of Reichenbach, I thought were a little shallow. But how he brings together with regards to the Schroedingerians is from the talk not too many episodes ago. It has that then the account then for quantum mechanics and the relativistic go together somehow in that way. The Lorentzians and the Schroedingerians. So back to classical mechanics, then there's the Newton and Galilean invariance instead of Lorentzian invariance. So time is not involved, and furthermore, rotation is not involved. Rotation is involved in any of these accounts except for angular momentum, an introduced or defined quantity. With regards to momentum, an introduced or defined quantity lost in the wash in this sense. So then the classical mechanics here has the account to reintroduce the rotational as its own kind of setting. It's unlinear is the idea. So that's about the vis-viva and the vis-motrix and the vis-insita, or the great controversial dispute between Newton and Leibniz that's not about calculus. It's not a priority dispute. It's like, well, we both agree we got calculus. This is the one for physics and mechanics. It's like we are not agreeing about the relational theory of space here for Newton's or Leibniz's account of the relational theory of space for a doubly objective relativity theory. That then this the account of the mechanics has it is inertial and kinetic. Then the kinematic is its own sort of account. Rotating frames are free, and there's real space contraction linear, and that's like entropy Leibniz's way. And space contraction rotational, which is kind of entropy Aristotle's way, yet it's totally not included in the theory. Relating these things together and comparing and contrasting these things. That then that's for accounts of motion, of course, which then get all the way back to classical expositions of the superclassical. So what's in topics in advanced quantum mechanics, imagine, is algebra and maybe a characteristic or index theorems, like Atiyah Singer. This is from the Addison Wesley Publishing Company, the Advanced Book Program, from UMass, University of Massachusetts at Amherst, Berry or Holstein, published 1992. Prologue, contraction of four vectors, be the metric tensor, Dirac matrices, Bjorken and Drell. And conventions of Bjorken and Drell. So he mentions the convention. So it's like, well, we're doing matrix mathematics, and then we're talking about vectors, and then also we'll be doing algebra on these results. But then when we talk about these conventions, is that also that's the shorthand for the implicits that otherwise get reduced away. So I'd be interested rather, if I say that, I can't but humbly assume that I'm not uninteresting, but I'm interested in this Bjorken and Drell with respect to Dirac matrices, who of course brings for Dirac's rule and law in quantum mechanics as theory, that I relate Dirac more to Planck with regards to a quantization proper compared to the mathematical accounts of the commutator relations and the and propagation laws. Those being derivative of the classical. So Dirac and Planck are quantum itself, and that's where it comes from. So the contents of these chapter names are propagator methods, scattering theory, charged particle interactions, alternate approximate methods, and it's got WKB, so that's considered accommodating the things. Semi-classical propagator, the adiabatic approximation. It hasn't been mentioned here quite the difference yet between the adiabatic and the non-adiabatic, and even the diabatic, which isn't really a word. It's always after the adiabatic. It's one way, like the heat equation with Schiller, and then non-adiabatic. It's like, well, in our electrical theory, we got to figure out how this current going on a wire is still electron holes moving back and forth. Non-adiabatic, that this is talking about these things. So WKB and Berry's phase and this kind of thing. The Klein-Gordon equation. So when I see Gordon, I'm pretty sure that it's truncating. It's reduced and truncating. The Zitterbewegung, and that reminds me of like the Brahms-Trillung, and not just because they're German words. The Dirac equation, advanced topics, and so the chapter 8 is advanced topics. Radiative corrections. Here there's the light is pure diffraction. Electromagnetic radiation is compounded refraction. They're not the same thing. And also, electricity is both high frequency and low frequency components. And light is in the middle of that in a sense. Spinless particles. So this is kind of like virtual photons. It's like, well, to take the place of a particle that have to propagate in this propagation equation, like scattering and tunneling, let's call it quantum electrodynamics, as Richard Feynman put it. Well, we got to have something here that does this. It's like, well, do they have mass? No. Will they have charge? No. They're just some amount of energy. It's like, well, should we call them nothinons? It's like, well, we can't really add a particle because everybody would let's just call them virtual photons. It's like, well, can you see them? It's like, let's just call them virtual photons. So radiative corrections here is accounts of this, and then the spinless particles is like massless photons and these sorts of things. Path integrals in quantum field theory. Here there's read that book from that great book on the path integral. That is reading from the path integral, that playlist there. Some years ago, we were still practicing kind of my voice and these kinds of things. Pion exchange and strong interactions. So pion physics, muon physics. That there's the kind of the electron, photon, muon, and hadron physics. 4 different things. So yeah, that's a book on topics in advanced quantum mechanics. The here is mechanics. Well, general readers, that's about the end of the hour today. This box of books then. Well, then I'll stack those books away and get out the next one from the next box in the next episode is the plan. Let's see what the first book is out of this box. Algebraic Geometry, a 3-volume series. So that'll be about algebraic geometry and the account of the different schools of algebraic geometry, because one leans on the side of algebra and the other leans on the side of geometry. And so geometry provides measure and analysis. So analysis kind of belongs to geometry. But it's in terms of algebra, and algebra is free in definition to make structures, and it's in the language of words. So arithmetic and geometry are considered as number theory and geometry, and they're primary. These are the structures. And then algebra and analysis are both derivative, and then they have the derivations in terms of each other and themselves. And the constructive account lives in algebra and analysis. But the definitions to make for the primary elements, or the primitives, the elements, the fundamental elements, the atomic elements, the non-degenerable or degenerate elements, these are about where then in these counts of infinity in arithmetic and continuity in analysis and infinity in algebra and continuity in signal or continuity in entropy or statistics or probability. In these accounts of language, then, it's all in theory. Warm regards. Good luck.